Pedro Vaz, who's going to talk about Verma modules and the Khovanov-Rozansky.
Okay, thank you. So thank you very much for the invitation. And today I would like to talk about HOMFLY homology. So we've seen in previous talks several flavors of HOMFLY homology through different constructions, and we know that HOMFLY homology has shown recently to have interesting connections with several subjects. For example, well, a fine theoretic algebras are connected with HOMFLY homology of torus links. Constructions connecting it with physics, commutative algebra, like we saw yesterday, people using circle bimodules, matrix factorizations, Hilbert schemes, we saw it yesterday. So some other constructions in algebraic geometry using some categories of sheaves over some algebraic varieties, and something that's called weight filtration. So this is one of the earliest geometric constructions of HOMFLY homology to Ben and Jordan Williamson. So I'm not trying to mention all names because I will leave someone behind. So I'm sorry if I don't say your name when you're here. And most recently, earlier this year, there was a preprint in the archive giving a construction of HOMFLY homology using the Egide-Fleur cube of resolutions. Moreover, in this paper by Dolin, I guess, he constructed a spectral sequence from HOMFLY homology to Egide-Fleur homology using these cube of resolutions. So okay, so there's a lot of interesting connections, but today I would like to give a different perspective on HOMFLY homology. So I want to talk about a construction of HOMFLY homology using two-representation theory. So as you know, two-representation theory studies actions of groups and algebras on categories rather than vector spaces. So we see a lot more structure going on than just using representation theory. And so to do that, we'll have a look at a very interesting construction by OL and Oel Kefelec and Antonio Sartori that is called the double Schur algebra. And we'll see that for knots and links, the HOMFLY polynomial has to do with something called parabolic Verma modules. So let's introduce this subject gently. So the idea of OL and Antonio Sartori was to put, well, the Eck algebra representation of the break group and the Jones-Ockniano trace, that were two somehow independent things, under the same algebraic structure. This way, they had a completely algebraic, unified description of HOMFLY polynomial. So that's how, in my understanding, they got the double Schur algebra. But you can look at it from, well, different perspective. You can see it, if you like, idempotent quantum groups. You can see it as an infinite dimension quotient of a certain idempotent version of GLN. So if you like idempotent quantum groups, so what you do, for each element in a weight lattice, you produce an idempotent, which is just projection onto this weight space, and then define your algebra as the idempotent truncation, in some sense, of your quantum group. Usually people use z to the n. It's the integral weight lattice. But nothing forbids us from doing just a translation of weights into see this inside a complex space, so you can see this inside some c to the n, and you can consider weights that are non-integral. So integral in integers shifted by complex numbers, if you prefer. So the machinery to produce idempotent versions of quantum groups also worked there, and as it turns out, the double Schur algebra is a quotient of this idempotent quantum group, which, differently from the usual Schur algebra case, this will be an infinite dimensional algebra. Okay, so let's try to define the algebra. So fix a formal parameter, call it beta. So here, lambda lk beta is just the weight lattice. So you see the first L entries are in some displacement of integers, so beta minus an integer, and the last k entries are just integers. So fix this alpha I is just the simple root as usual, and now you can define the double Schur algebra, which depends on parameters q and beta and two integers L and K as a linear category, which is defined by the following data. So the objects are just these projections, these one mu's. So are you can see it as they are in bijection with the weight lattice together with the zero object. So morphisms are generated by E's and F's as usual. And you know that EI moves from the mu weight space to the mu plus alpha i's weight space. That's what's written here. And F this goes the other way around. We consider the identity, and then as usual we impose relations. Okay, so first relation says that these one mu's form a family of orthogonal idempotents. The second is the usual commutated relation that you know from GLN. So we have some other relations, and we impose that the identity of mu on mu is 0 if mu is not in the weight lattice. So this is the Schur quotient. Okay, now if you look at the definition of the Schur algebra, you know that you see that the Schur algebra, the usual Schur algebra, embeds in the double Schur algebra. So the name double means that we have two copies of the Schur algebra. And through the embedding of the Eck algebra into the Schur algebra, so this 0k is just the usual Schur algebra. Through this embedding, we can define an action of the braid group. So as usual, it sends a crossing to a linear combination of some elements in the algebra. But we can turn these elements in pictures, and there's a gadget called ladder operators that goes through skew duality that most of you know very well. This can be given a nicer description. For example, so the idempotent one mu we write just as vertical parallel strands, but now the first, well, here you have k strands point down, and the last k point up. The operator EI, we just put a ladder. So this is somehow horizontal segment between two vertical strands, and this is regardless of the sign of these i's and I plus 1. Depends on where you are, left hand side or right hand side. And for F, you do the other way around. And let's see. relation, this assignment can be written somehow as sigma I is sent to something q minus 1 to 1 beta minus 1 k. We have this minus, and now we have fi ei. And here we have E points to the left. So these diagrams should be familiar from several of the previous talks. And use the explanation. This gives the explanation of why people are using webs over and over. It's just diagrammatic description, presentation of these formulas. Okay, so now we can consider closing braids. So let's close them to the left. So applying this to all crossings in our braid produces a web diagram. Same type of Paul and Dave and others explained, which is closed. And the pattern goes like this. So you have one web diagram, and then you close it like this. Okay, everything points to the right. Oops. This comes to the left. And so here you have beta minus 0, it's the label, beta minus 0, beta minus 0, and here you have 0, 0, 0. Okay, then we get linear combination of these elements, and this element, each of these elements is an element of the double Schur algebra. Okay? Then you take linear combination of all these guys. So this gives an element called S of B, which lives in the double Schur algebra. And what OL and Antonio proved is that this element is a multiple of the identity for this. Wait. Moreover, they proved that the coefficient, so it takes the identity to some multiple, the coefficient is the HOMFLY polynomial of the closure of the braid. Now, this is very interesting, okay? Just somehow slightly different construction of the HOMFLY polynomial, but we can try to see it from a different perspective. So instead of looking at this guy as, or a linear combination of these guys coming from the braid, as an element of the Schur algebra by itself, you can take this element and let it act on a module for the double Schur algebra. Then we'll start seeing something different. So let's see what I mean with that. So let's define lambda plus through these two conditions. So this is the analog of the positive weight lattice for this case. Everything I'm showing here, if you put the first parameter L equals 0, reduces to what we know about the Schur algebra. And the other way around. If you put k equals 0, everything reduces representations of the Schur algebra. So we can introduce a total order on the weights. The most, well, usual way. And now, using this order, you can define Weil modules. So highest weight modules for some mu in the positive weight lattice. We can define Weil module by the usual quotient. So you mod out by all weights that are above mu in this total order. So this is what this means, the ideal generated by all these elements. Okay, so it has a highest weight category, and Oelis and Antonio give us an element we can act on a Weil module. And which Weil module? Well, the one corresponding to this highest weight here, to this weight. So you see it, I'm just rephrasing the same things in a slightly different language. So we can rephrase the result and say that the HOMFLY polynomial is the coefficient of the highest weight vector on this Weil module under the map. Same thing, different words. Okay, but now comes the novelties. So we have the double Schur algebra, which is a quotient of some GL K. So you have a module for the double Schur algebra. So it will also be a module for GL to K. So that means that GL L plus K in general acts on these Weil modules in the most obvious way. And as it turns out, in this particular case, well, it's more general, but the case we're interested, as a module over GL, let's say 2K, K strains going up, K strains going down, is what it's known. It's what we call a parabolic Verma module. So now we can use representation theory of GL to K to study HOMFLY polynomial. So let's see what is a parabolic Verma module. So I will not go into technical details. I'll try just to say enough for us to keep on going. So we consider a parabolic subalgebra. So this means that a subalgebra that contains a Borel. So if you like to think in terms of matrices, so a subalgebra that contains upper triangular matrices. And for the experts, everything is standard. So standard Borel, standard parabolic. I will not do anything outside this setting. So then there are two factors we can construct out of the choice of a parabolic subalgebra called the Levi factor, and there's some nilpotent radical. We take an irreducible finite dimension representation of the Levi factor, so this is a Lie algebra, and extend to the parabolic. So this generalizes the usual notion of Verma modules, inducing from the Borel subalgebra. And now you define the parabolic Verma module associated to P and V as the induced module. So if we have P equals B, the standard Borel, you get the usual Verma modules. Go. and we only consider V finite dimensional. There seems to be some, well, for me, some confusing terminology. What I mean parabolic is when V is finite dimensional, but you can consider V infinite dimensional, and then we call it a generalized Verma module. So I'm try to keep things simplest as possible. Okay, now let's define a parabolic for this case. So let's index the simple roots by 0 to, so from minus k plus 1 to k minus 1. And to define a parabolic, let's just join all these Chivalry generators to the Borel. So you see we left F0 out. So we join everything except F0. Remember that F0 are the guys here. And you have is. So now, as a module over GL2K, the wild module I just sketched there is isomorphic to this parabolic Verma module, where we induce from a one-dimensional representation of the Levi factor. In the one-dimensional representation, it's generated by a single vector in this way. Okay? So now you can rephrase again OL and Sartori's results, saying that the HOMFLY polynomial of the closure of a braid is the coefficient of the image of the highest weight vector in this parabolic Verma module under the QS map. So I'll make Kefalex Sartori short and just say QS. I hope you don't mind. Simpler. Okay, good. So now that we have this different perspective, one can ask, well, let's try to categorify the HOMFLY polynomial using this picture. So what do we have to do? Well, first we have to categorify this parabolic Verma module. Second, we need a way of turning this guy into a chain complex. So just pass to some category of complexes on the categorification of the parabolic Verma module, and then you have to prove you have the HOMFLY polynomial. Okay, so the idea is to find a nice category. Let's call it MP, which has some block decomposition. So this under the direct sum symbol, just the support of the module. That means that for each weight that you can read out of these horizontal lines gives rise to a block in your category, so the block of your category, and you need functors to move between blocks. So functors E and F and K. And, of course, you want to have the right action, you want them to descend to the right action, to the correct action of GL2K on the Grothendieck group, so that you have an isomorphism of representations. Okay, first thing, if you know anything about Verma modules, or if you look at this formula, where is it? Here you go. This formula 2 here, remember that mu's are written in terms of betas, which is a formal parameter, and we can think as q to some exponent, some complex number, and integers. So this guy is not integral. This is a rational function of the form, well, surprise, surprise, of the form, for example, lambda q minus 2 minus lambda minus 1 q2 over q minus 1, where the lambda is q to the beta. So right here we see something different. So we need to be able to categorify this denominator. Moreover, we need something bigraded, have a minus. So the way one way to see these minus signs is that we go to the superworld, work with the supercategory. That on the Grothendieck group, the parity will descend to this minus sign. And there's no way you can get rid of the denominator. So you need to work with infinite objects in a certain sense. So I'll learn more about that very soon. Okay. So one place to look, try to generalize scalar algebras. They're very, very nice to handle. It's easy to learn to work with them. The description is simple and natural, so we can try to generalize scalar algebras. So for a choice of parabolic subalgebra, we can try to define a version of the scalar algebra. So let's go there. Okay, now let me define it. So let's consider that you have some algebra. So nu here is just a weight element. Let's consider, well, you have these usual scalar generators, dots and crossings for all simple roots I and j, and let's add a new generator, which we call a floating dot. This blue bubble here in a region that can float within regions. Moreover, we think of floating dots as associated to the simple root alpha 0. Alpha 0 is the simple root that corresponds to this line in the middle, where you stop having betas and you have only integers. Moreover, they can also be labeled by non-negative integers. So actually, we can go without this extra amount of information, but as it turns out, formulas that are complicated and things that are hard to prove are easily done, allowing this, enlarging this set of generators. Good. So now, let's, in the spirit of KLR, define a K-superalgebra, defined by K-linear combinations of these diagrams, where the multiplication, as usual, is concatenation of diagrams if the labels agree, and 0 otherwise, and module isotopies that don't change the height function. Let's see why. So I mentioned we needed a superalgebra. So let's say that KLR generators are even and floating dots are odd. Simplest thing to do. Okay, now we impose relations. So we want to extend the KLR algebra. So let's impose the KLR relations on the KLR generators. For if you don't have floating dots, nothing changes. Just the usual KLR algebra. But relations involving floating dots change things drastically. Now, the first relation says that floating dots anticommute. Second tells you how to slide floating dots to strands. See here the labels are changing. And this is in the case of the parabolic we fixed. Adjoin all f's except f0. And now, the third relation, things get a bit different. So this is sort of randomized to position with some floating dot inside. And to remove the floating dot from this region, it costs you two diagrams. Floating dot on the left, floating dot on the right. Notice there are no sliding of floating dots through crossings. The only way you can get rid of floating dots in a region with crossings is to use either this or this. So that from the technical point of view makes things harder, because usually what you do, well, in this world of diagrammatics, you try to slide all extra information to the bottom of the diagram so that you get dots, possibly floating dots, and crossings, limitations, so that you easily find a basis. This is not true here anymore. They don't slide, they get stuck. Nevertheless, we have bases. It's harder, but we can deal with it. We have a very special basis I will mention later.
What does the green mean?
Sorry?
Why are some of the things green?
Oh, green is the root. So, this is the simple root alpha 0, corresponding to this. These guys are the roots alpha 1 and alpha minus 1, so the neighboring. So if you look at, so I have green. So you can see this, I will draw it here. Locally, the linking diagram is like this. Type A. Okay? Yeah, I forgot to say this. These are the simple roots. Okay? Last relation, if you have a floating dot to the left of all strands, the diagram is 0. Okay. First thing, we have a representation of this algebra on a supercommutative ring, so polynomial ring tensored with an exterior algebra. The action is faithful. Moreover, the algebra is bigraded. I can say something about the grading. So in some sense you respect, you already know the parities. Here. The degree as usual of a dot is to 0. And here you have the Q grading first, and then the lambda grading, the new grading. I think it is homological grading. So the degree of a crossing ij, let's say it's 0, 0 if in the linking diagram I and j are far apart. As usual, it's 1, 0 if ij is formed, and it's -2, 0 if I equals j. So we don't do anything to the KLR generators. So the grading is extended trivially. But for floating dots, things change drastically. Okay. So let's write the degree of a floating dot labeled A is given by twice 1 plus A minus L0 plus L plus minus. So this is the Q grading. Into, I would say, what is that? So I want to emphasize some aspect here, some feature. So A is the label, L0 is the number of strands labeled 0 at the left of the floating dot. So for example, like here, for this guy, L0 would be 1. L plus minus is the label, the number of strands labeled plus and minus 1 at the left of our floating dot. Like here, it would be 1. So you can compute, supposing that there's nothing at the left, you can compute easily the gradings of the degrees of the floating dots. But the important feature is that this is non-local. Contrary to usual KLR algebras, where things are defined locally, you don't need to know where you are. Just look at the generator. Here, it's not true anymore. Okay. And using these gradings, one can check that the relations respect the grading and the parity. Okay, but what we really need to know, to use, is a certain cyclotomic quotient of this Kähler algebra. So let's define the quotient of the algebra, Rp, by the two-sided ideal generated by all diagrams whose first strand on the left is not 0. It's not labeled 0. So it parallels the fact that in the parabolic Verma module, some f, which is not f0, acts trivially on the highest weight vector. You can see it from the definition. Okay, now if you're wondering what if this works, does it work for other types of quotients, other types of parabolics, other types of Lie algebras? That's true. So for every parabolic algebra, for every symmetrizable Katsumudi algebra, and for every V finite dimension representation of the Levi factor, we have an algebra like that. So we have R PG of V. That categorified. So this should be out right after the summer, right?
Yeah.
So it's written, we're fixing some stuff, it's ready. So here we have categorification of all parabolic Verma modules, in particular all Verma modules for all symmetrizable types. And it's easy to guess from what I've shown now. The hard part is to prove it's that. Okay, so let's define the category we're working. We have an algebra, superalgebra, and I will always say algebra. Sorry, I will cut super from everything. Everything will be super. Okay, so let's take category of left-bounded locally finite dimensional supermodules. So what does that mean? Okay, left-bounded, say gradings are bounded from below. Locally finite dimensional means in every degree the modules are finite dimensional. So I mentioned that we needed to work with infinite dimensional objects. With degree 0 morphisms, well, and take the sum of all these categories. Now take our p beta of v, so modules, as a categorification of the new weight space of this parabolic Verma module. So now we have a candidate for the weight spaces. We need to define functors to move between them. As usual, if you have a diagram, you can add a strand labeled I at its right, and this will define induction and restriction functors between the categories of modules. Let's call one F and the other one E, and throw in some shifts. So this is the usual recipe. Now, there are several relations involving these functors. For example, there is a short exact sequence of functors. Well, there. So what do I mean by that? So first, E and F are defined. This is on the weight space nu. Q, you can think of Q as the functor of tensoring. We work over a field K with a polynomial ring with some shifts, so that in the Grothendieck group will descend to multiplication by 1 over Q minus 1. So what we are saying there, the first relation says that on the Grothendieck group we should have the commutator E0 F0, so E0 F0 minus F0 E0 should be what's on the right hand side. So first term, you know, 1 over Q minus Q inverse, some shifts in the Q grading and in the lambda grading, plus some big pi. So this is the perishift functor. It's the minus 1 we were looking for, times almost the same thing with different shifts. So if we call this grading shift functor K, the other one is the inverse. So this would give K plus pi. Pi is minus 1. K minus 1 over Q minus 1 applied to the same weight space. So this is the commutator relation for E0 and F0. And here, I need to stress, we don't have the usual direct sum decomposition. We don't have this guy would be the guy in the middle would be the other guy, direct sum with copies of the identity. This cannot happen. First, if this would happen, let me explain right away, we could use the maps of the decomposition to prove that E0 and F0 would be bi-adjoint. Now, bi-adjointness can be interpreted as the symmetry that exchanges E and F. If you look into a Verma module, they're not symmetric. F can go forever, but E can't. In this case of parabolic Verma module, this only happens with F0 and E0. So they cannot be bi-adjoint. Moreover, this exact sequence does not split. Okay, for the other roots, we have the usual stuff, right? direct sum decompositions. So this is already been done before. So it's just a matter of juggling a bit with the proofs of Aaron and Michael to get these relations. The other one is harder. Okay, so what more can we say? So functors EI and FI are bijoint. It's clear. For I not 0, and E0 and F0 are exact and form an adjoint pair. We need exactness because we want a map on the Grothendieck group. Okay, so now these functors induce an action of UQ of GL to K on the Grothendieck group, and we get an isomorphism of representations. So we have categorification of this parabolic Verma module. Good. First part is done. Now you have to construct link homologies. Okay, so now we know from the presentation before of the braid group action, we know that we have two copies of the Schur algebra going up and going down, and the braid group only acts on one part. In particular, if you remember this picture, so this corresponds to root alpha 0. This one goes up. The braid group will only act here, and it does not involve F0 nor E0. These two functors are only used to close the braid. From the bottom with F's, from the top with E's. So that means we can use the fairly used recipe that turns the representation of the braid group into a chain complex by Ricard, and define the complex as written there, where the chain map is just the unit of this adjunction EIFI. So this is well known. This was known before, and automatically we have a braid action in our category. Well, if you work in a category of complexes, of course, module homotopies. There you go, here. Okay, now we have a braid action. This is other person's work. We consider the closure. So the closure gives you a functor that you can apply to the block corresponding to the highest weight category in your categorified parabolic Verma module. So this is just C. So you get a functor that takes C, for example, and spits a chain complex of C vector spaces. Locally finite dimensional C vector spaces, graded, by graded. So now you have a way to produce a chain complex, and one can prove directly that the homotopy type of this chain complex is invariant under the Markov modes. So it's a link invariant. Moreover, the graded Euler characteristic is the HOMFLY polynomial of the closure of the braid. So you have a categorification of the HOMFLY polynomial. This we prove when we have a braiding, so we have to check that you respect, on the Euler characteristic, you respect the Skine relation and the value for the R0. And I forgot to say was that I don't know where I used to be, of the R0 is not 1, so it's unreduced. So this is for unreduced. I can do reduced as well, but let's Keep it as it is. And moreover, we can prove that these triply graded groups are isomorphic to Khovanov-Rozansky's triply graded link homology. So this is a weak isomorphism, I have to say. So we know that the bigraded dimensions are the same. Well, the triply graded dimensions are the same. We don't have a functor between the two constructions. It's sort of what we could do. Okay, now we can think of categorifying other Khovanov-Rozansky homologies. So we need to know how to project your parabolic from a module into a finite dimensional representation in terms of two representations, in terms of the categorifications. So for each n, let's introduce a differential in our algebra of b degree 2n minus 2 and parity 1 by declaring that it acts trivially on crossings and on dots, doesn't do anything to KLRs. It only sees floating dots and sends a floating dot to this polynomial on dots. So H is the complete symmetric polynomial, E is the elementary symmetric polynomial, and as before, well, A, you know, L0 was defined before, L plus minus 1 as well, so here's the formula that you have to place at the same height as the floating dot. Just give a small, short example. Green. So if you have this diagram, so this is label 0, this is label 1, 0, and some, I don't know, 5. And you put a floating dot here. Let's take d2 of this. So this would be, let me just draw it before. First terms are 2 dots here, a dot here, a dot there, 2 dots there. So this is m equals 0 because L plus minus 1 is 1 plus here and here and here and there. There you go. So they're not that easy to handle. So this is a simple, very simple case.
What does it mean to take H of L0 in the formula?
Sorry, I didn't understand.
It's H of L0.
Oh,
Complete symmetric.
this is the complete symmetric polynomial
And what's the L0?
on the L0 on dots, only on L0 strands. Sorry, like here. Okay? And this is the elementary on dots only on the L plus minus strands, like the ones in green here. Sorry, I forgot to say that. Okay? And there should be a sign. Yeah, forget about the sign. It can be added and removed at will. Okay. Now, one can check that after introducing this differential, we get a DG algebra which is quasi-isomorphic to a cyclotomic quotient. Cyclotomic KLR that is known to categorify finite dimension representations. Let me just see what happens. So you have n, 0, 0. So this is GL 4. But for SL, this is where we know KLRs, right? I'm just interchanging between GL and SL weights. So we have 0 and 0, as it should. And this is important because now we can pass to, well, a suitable bounded derived category and categorify Khovanov-Rozansky SLN homology out of this cyclotomic quotient. So this comes from the previous work on web algebra by Makai Yonezawa, that it will be Khovanov-Rozansky on the nose. Okay, good. Now we can also consider homology, the differential coming from the chain complex, and this Dn altogether and form a bicomplex, which gives rise to two spectral sequences, the bicomplex, double complex spectral sequences. And in fact, we can inspect and check all the gradings of the differentials and see that these are in fact, well, versions of spectral sequence constructed by Jake in 2006. Notice we are doing erased unreduced homology. Now, this differential is formal. I didn't say how to check it, but we use the basis. There's a special basis we can define to prove that this differential is formal. So it will induce a formal differential on HOMFLY homology. This one can check by diagram chasing, and then moreover, we have a formula for the differential here, and we know that the chains in our complex are polynomial rings tensor with exterior, so floating dots. And we know that our differential, the n, only sees floating dots. So juggling a bit with diagram chasing, studying what happens on cycles, because you know the differential of the complex, one can check that the differential it induces on HOMFLY homology is formal. So that means that homology is concentrated in a single grading, so the lowest lambda grading, which already we can compute from our construction. We see that everything, the lambda grading and the homological grading, they fit into a rectangle. So the homology of this, the n, will be concentrated in a single lambda grading, if our computations are correct. This means that when looking at the spectral sequences, there are no further differentials. That is, the spectral sequence, both spectral sequences converge at the second page. So this is the matter of looking, tracing what's going on, in particular in the lowest lambda gradings. That is, we can say that Khovanov-Rozansky homology is the homology of HOMFLY polynomial, HOMFLY homology with respect to the differential dn. And, well, that's a nice thing to do with higher representation theory. That was our motivation from the start. So I discussed this with some people. Oh, I have a new construction of HOMFLY homology, but I don't want to write it because it's just HOMFLY homology. And at some point, people write it. It might give new ideas to people. And at some point, I met Paul, and I say, oh, I have just the definition. I don't want to do anymore. Anything else? It's fine. I'm cool with that. I want to do Verma modules and then categorify all Verma modules, and then this HOMFLY homology is old. And Paul pushed me. Well, we have to prove that is Khovanov-Rozansky. And if it's Khovanov-Rozansky, study the spectral sequences. And then, well, it worked fine. Everything is correct, of course. And, well, that's it. That's a nice story. Thanks.
Questions for Pedro?
Is there any hope of constructing sort of other differentials corresponding to?
I looked a bit at D0 and D-1, and then I don't know, unless I have a different look at the algebras we use, because these are recent algebras, they're not very well studied. So perhaps, maybe in connection with what Dave said the other day, this mirror, maybe you can try to reproduce this mirror, because you can rewrite these extended KLR algebras in slightly different ways. The algebra is not unique. By the way, I forgot to say, these categorifications, if you impose some conditions, are unique. And the conditions are this algebra acts there, as you have to impose something. So I don't know. I have to look at the algebra from a different angle. Perhaps I think these ideas might be helpful. I forgot to say, let me just say one small thing, how to do reduced homology. Okay. Like this. This is what I did, right? So to do reduced homology, you just get rid of one of the strands. So you have k and k-1, and just consider the highest weight beta-0, beta-1, and 0. You do the whole same machinery, just change the highest weight. Same parabolic, different highest weight.
Do you have do you have differentials that turn on the cyclotomic quotients, like other cyclotomic quotients, and more general? So this was sort of a type A differential that you.
Yeah.
If you start with the more general kind of picture with floating dots of.
Yes, we have, and it depends on it. They're not defined the same way. They are defined on this special basis that I've mentioned. So let me just see one small thing. So we have a basis where all floating dots are in the first region. The basis is more complicated because, well, you can have diagrams like this, and here you put a bunch of dots, okay? The important is that there's a basis where all floating dots are in the first region, and we can tell where to put them. We use this gives a basis. We use this basis to compute the dimension of the algebra, which agrees with the predicted by the Shapovalov form on the module. So the bigraded dimension of the algebra is the Shapovalov form. And to answer your question, the differential here, if you have the floating dot in the first region, there's only one strand at its left, right? So the formula becomes much easier. So send this floating dot to a bunch of dots in the first string, the same place. And there's your answer. And it was 4 times, so it gives on the nose all cyclotomic quotients.
Maybe one more short question.
Sorry, could I have a quick one then? Just going back to your beginning, you were working with braids. You were handling braiding on the K strings at the right, and presumably you can handle braiding on the K strings at the left. Does this model let you do anything about mixed braiding?
Yeah. So
between the up and the down string.
2 braids at the same.
No, where you cross.
Switching.
Where you in effect take a 2K braid with some strings going up.
Oh,
and some
okay.
strings
Oh,
going
okay.
down.
Good. So
Then
you mean
closed. So you get a flap rather than a closed braid.
a crossing here?
Yeah, something like that.
Here there's a problem. We have a problem because I don't know how to define the complex. Because the complex is defined in terms of E's and F's.
Okay.
And
And the original stuff, the double sure, whatever algebra,
Yeah.
would handle that. But
I don't think so. So L is the expert in the double sure. For my point of view, doesn't.
Of categories that allow you to switch the order of the ups and downs, but they don't live in the same big category.
yeah.
It is all, everything here lives inside, well, this while module, and I don't know what to assign to this sideways crossing.
Okay, I suggest we discuss further questions over coffee, and we convene at 11:30, but before that, let's thank Pedro again.